All right, guys. So today we are going to move on to two sample mean problems. Okay. So we're going to do a complete four-step process for one of these questions, and then we're just going to discuss briefly the differences that you'll see in a second question. So go ahead, download this if you haven't yet. Take a second and go ahead and read this question, and then we can go ahead and get started. So first of all, I want you guys to realize that this is going to be a two sample mean question because we are ending up taking a random sample of babies that use walkers and then a sample of babies that have never used walkers. So this is a two sample problem. More importantly, we are talking about averages. So this is a two sample mean problem. Next, usually we have to decide between Z and T. Now, I want to make sure you guys understand that we are going to use T-scores, but the reasoning is not because it's averages. All right. The reasoning that we're using T-scores, okay, the reasoning that I want y'all to have is because if you look at this problem, the standard deviations that we have, are from our samples. We use T-scores whenever we have the sample standard deviation, or what we denote or annotate as S. Okay, that's the letter that we use for the sample standard deviation. If we knew the population standard deviation, which we call sigma, if we knew the population standard deviation, then we would use Z-scores. But it is pretty rare for us to know the population standard deviation because if we knew the population standard deviation, we would probably know the population average. And if we know the population average, then we're not having to infer anything. So last but not least, it says that we are doing a 95% confidence interval. So CI. So we're performing a two sample mean T confidence interval. Now, what is our goal? So remember, whenever you're doing two sample problems, it's not just that we're trying to find the two population averages, it's that we're trying to find the difference between the two population averages. So we're trying to find, if you look in the problem, it says the difference in mean mental scores between babies who use walkers and babies who do not use walkers. So let's say mu sub W for the average mental score of babies that use walkers. And let's say mu sub N for the babies that do not use walkers. And again, we're trying to find the difference between these two averages. And in math, the way we find the difference is by using the operation subtraction. All right, so we're trying to find mu sub W minus mu sub N. But if someone were to randomly stumble across your question, they might not know exactly what you mean by mu sub W and mu sub N. So let's go ahead and define those things. So where mu sub W is the population average mental score of babies who use walkers. And mu sub N is the population average mental score of babies who do not use walkers. Again, you can call this mu sub 1 and mu sub 2, but I like to use the letters that help guide me. I'm never going to forget that mu sub W is the walkers, and I'm never going to forget that mu sub N is my babies that don't use the walkers. Give me 1 second. Okay. All right, so that's step number one. Name the process that we're doing and then define what the goal is using the context of the problem. Step number two is we need to make sure that we check our conditions. And the first condition that we always like to check is that we have taken a simple random sample, except we're not taking one sample, we're taking two samples. So we want to make sure that we have taken two separate simple random samples. Let's look back at the question. I know it's a little bit wordy, but let's see if we can figure that out. So it says one study compared a mental skills of a random sample of those who use walkers with a random sample of those who never use walkers. So we're going to put stated random sample of those who use walkers and random sample of those who did not use walkers. So we're just verifying that the problem has stated that we have taken, oh, sorry guys. So we're just verifying that the problem has stated that both of the samples that we took were randomly selected babies, okay? I don't know how exactly they did that, but we're gonna trust the problem. All right, next, we need to make sure that our distributions are both normal. Now, when we did our one sample means, we had kind of three processes to use. So we can either look for the problem and it will tell us that the population is normal. And if the population is normal, then our sampling distributions will be normal. We can check by using the central limit theorem, which says as long as we have a big enough sample size, we're good enough. Our sampling distributions is going to be approximately normal. Or we're going to have to graph the data. And that is usually the longer process. So hopefully we don't have to do that one. So look back at the problem. Look back and read the problem. Do you guys see anything on there that says that the population is approximately normal or anything along those lines? I don't see anything like that. But what about the sample sizes? So what is the sample size that we took for our babies that use walkers? Let's see if we can find that. So 54 babies were taken. So our sample size, so my sample size for my walker babies is 54. And the sample size for my non-walker babies, how many non-walker babies did we take? We took 55. Remember, the sample sizes don't need to be the same. It's perfectly acceptable that they're different. So here's what we're going to put. Both sample sizes are greater than 25 by the central limit theorem. Both sampling distributions are approximately normal. All right, so we got to use the central limit theorem. Both our sample sizes were big enough, greater than 25. And since they're both bigger than 25, both our distributions are going to be approximately normal. All right, awesome. Up next, we need to check the 10% rule. Usually you don't need to check this if you're doing like an experiment, but we're not doing really an experiment here. We're sampling these babies and checking out their essentially their cognitive ability, their mental scores. But we need to just check the 10% rule for both. So 10 times my sample size is less than the population. Since we're doing a two sample problem, we check this both for both our samples. So 10 times my sample size for my walker babies is less than the entire population of babies that use walkers. So 10 times 54 is 540, which is less. I'm going to assume, I don't know a whole lot about babies, but I'm going to assume that there is more than 540 babies out there that have used walkers. So population of babies who use walkers. All right. Then we make sure that we check for our other distribution, our non-walker babies. So 10 times my sample size needs to be less than the population size. Well, 10 times 55 is 550, which is less than the population of babies who don't use a walker. All right. Those are the three conditions that we always check. But when it comes to problems that deal with means, if you have used t-scores, you need to state your reasoning for using t-scores, and it's always the same. The whole reason that we use t-scores is because we're going to be using our sample standard deviations, the standard deviations from our sample, not the population. All right. And it's very, very easy to check that. All we have to say, we're essentially saying, hey, grader, here's why I'm using t-scores. I'm using t-distributions because we are using the sample standard deviations. All right, so I know it's a lot of writing, but this right here, if I show you guys the entire page now, this is going to be the expectation for step number 1 and step number 2. It's a lot of writing, but by now we should be so familiar with inference that it's almost second nature. We're just checking everything essentially twice from what we learned on Friday and what we talked about on Monday. All right, I'm going to flip the page so that we can do our math step. All right. Every confidence interval ever starts out as statistic plus or minus the critical value times the standard deviation. All right, that's typically how we always start out. But when we're doing one mean, if this was a one mean problem, we would say our sample mean, which we call X bar, plus or minus the t-score. Now remember, when you write out your t-score, there's two things you need to look out for. The percentage of your confidence. So like if you're doing a 90% confidence interval or a 95% confidence interval. And then you also need to put your degrees of freedom, which is your sample size minus 1. All right, then the formula for standard deviation of a for one mean problem is S over the square root of our sample size. So the sample standard deviation divided by the square root of our sample size. That's what the formula would look like if we were doing a one sample mean problem. So I want you guys to go ahead and pause a second and see if you can figure out what the formula is going to be now that we are doing a two sample problem. While you pause, give me 1 second. I'll be right back. I'm going to try to pull up the formula chart. Okay. So actually, let me go to my, actually, I'm going to pause the recording and I'll pull up the formula chart. Okay. So just give me 1 second. All right. So hopefully you guys took a look at it and maybe you got an idea exactly of what it is that I'm expecting of you guys. So since we're doing two sample problems, we're going to have a sample mean for our walker babies. We're going to have a sample mean for our non-walker babies. And remember, it is the difference between them that we are trying to find. All right. Then we're using t-scores. According to this problem, we want to have 95% confidence. Now, here's one of the first changes. How do I find the degrees of freedom if we're doing two samples? Which sample size am I going to use? Well, this is kind of a weird process because if you're using the calculator, it'll find it for you. But not everybody has that TI Inspire. So I want to make sure that y'all understand we're going to use the smaller sample size for our degrees of freedom. So the degrees of freedom, if you're being careful, you use the smaller sample size when you're doing a two sample problem. So look back at this question. We had a sample of size 55. We had a sample of size 54. So 54 is technically the smaller sample size. And if we're doing degrees of freedom, it's 54 minus 1. So our degrees of freedom would be 53. All right, it's a little bit odd. It's not perfect, but if we're doing it by hand, it's going to be acceptable. All right. Next, this is why I wanted to pull up the formula chart for you guys. I want to show you, this is not something you will need to memorize. It is on our formula chart. So I'm just going to pull it up here. When you're dealing with means, so right here's the word means. If you're dealing with two samples, then we're going to use this as our standard deviation formula. But we actually technically don't have sigma. We don't have the population standard deviations. We have the sample standard deviations. So we're going to use this formula right here for our standard deviations. So S1 squared over N1 plus S2 squared over N2. Let's tie that to our specific problem. So let's go back to our problem. All right, so we take the square root of the sample standard deviation of my Walker babies, and we square it, divided by the sample size of my Walker babies. Then we add to it the sample standard deviation for my non-Walker babies, and we square it, and we divide it by the sample size of my non-Walker babies. I know it's a lot of annotating going on. That is okay. All right, now that we have it annotated, now we can go to the actual problem, and we can try to start filling in some of this information. All right, so what was the average mental score for my Walker babies? So it says they averaged a 113 mental score. What about the average score for my non-Walker babies? It was a 123. All right. And we can actually do this math real quick. 113 minus 123 is, be careful, it is -10 because it's a smaller number minus a bigger number, that's -10. All right, what about my t-score? So we go to our handy dandy t-chart, and we need to use 95% confidence, and we need to use a degrees of freedom of 53. So let's go to our t-chart, and let's start with our degrees of freedom. Uh-oh, guys, look at your degrees of freedom column. I don't see 53 on here. Well, we got to use whatever is closest. So we're going to use 50 as our degrees of freedom, and we are doing a 95% confidence level. So where do those two intersect? At 2.009. So the t-score that we're going to use is 2.009. All right, then for my standard deviation formula, we got the square root, the standard deviation for my sample of Walker babies. So my Walker babies had a standard deviation of 12. So we have 12 squared over the sample size for my Walker babies, which was, we took a sample of 54, plus the sample standard deviation for my non-Walker babies, which is 15 according to the problem. We square it, and then we divide by the sample size of my non-Walker babies, which was 55. All right, remember the part that is after the plus or minus is called your margin of error. I like you guys to calculate that all at once. So I'm going to pull out a nice TI Nspire. Again, you don't need the TI Nspire, but I have uploaded for you guys a link so that you can download it. So 2.9 times the square root of 12 squared divided by 54 plus 15 squared divided by 55. So my margin of error is 5.22. So we have our statistic and we have our margin of error. So now to get our lower bound and our upper bound, we simply do -10 minus 5.22, and then we do -10 plus 5.22. So -10 minus 5.22, we get -15.22. And then we do -10 plus 5.22, and we get -4.78. All right, so we have now found our confidence interval. And now to close up shop, we always start out with our cookie cutter sentence. I am 95% confident. And what is it that you just found? Well, you can always go back to step number 1 and put this into words. This is what we just found. The average for the entire population of walker babies, the average for the entire population of non-walker babies, and we are finding the difference. So we just need to put that into words. I'm 95% confident that the difference in the population mean mental score until scores of babies who use walkers and babies who do not use walkers is between negative 15.22 and negative 4.78. So that's a pretty cliche, a pretty go-to cookie cutter sentence. Again, what is it that we just found? And we believe it's this, between this number and this number. Now, guys, again, what I want you to realize is mental scores cannot be negative. You can't have a negative 15 mental score. You can't have a negative 4 mental score. That's not what it's saying. All right. What it's saying is if we subtract the average mental score of a walker baby from the average score, oh, sorry, not from the average score of a walker baby and the average score of a non-walker baby, their difference is negative. And we'll talk about what exactly that means when we answer part B. Okay, so looking at part B on your question, we have now answered part A. Part B says, is there evidence, so does your confidence interval support the belief that walkers affect infants' cognitive development? We want to explain our answer. So again, what I want y'all to realize is we just took the average walker baby score, we subtracted the average non-walker baby score, and look at our results. We believe the results are somewhere between negative 15.22 and negative 4.78. What I want y'all to realize is that all of the numbers in between these two are negative answers. Now, wait a second. If you subtract two numbers and you get a negative result, what does that mean for your two numbers? All right, hopefully you can answer that. Really think about it for a second. If you subtract two numbers and you get a negative result, it means that the first number is small and the second number is bigger. A small number minus a big number is a negative answer. So based off of our confidence interval, we have proof that walker babies have a smaller mental score than non-walker babies. And that's exactly what we're going to put. Since our confidence interval is composed of only negative, oh, that sounds fancy. I'm getting fancy on this answer. Since our confidence interval is composed of only negative results, only negative numbers, we believe the average mental score for babies who use walkers is less than the average mental score of those who do not. So that's a pretty, sorry that I kind of got off there. But you guys need to be able to understand what your confidence interval results mean. All right. Since we got negative numbers only as our answers, it means that we think the first number is smaller than the second number. Well, and since we did walkers minus non-walkers, we think the walker babies have a smaller or less mental score than the babies that do not use walkers. All right. So that's kind of the game plan here. I just want to show you guys this one question right here. This is a great question. Question number 12. It is trying to compare female and male sophomores and the average amount of time that they study in a week, essentially. Couple things here. They have given me my sample sizes for both genders. They've given me my sample means for both genders, and they've given me my standard deviations for both samples of my genders. The step I want to talk about is my normal step. Now, nowhere in this problem does it say that the populations are normal, so we can't use that. And if you look at the sample sizes here for my two samples, they're not above 25. So we cannot use the central limit theorem. And we don't have every single individual student. Like, I don't know how long each individual student studied for, all 15 females and all 19 males. But what they have done for me is they have graphed the distributions for me. Again, when you're graphing the distributions, here's what you're looking for. Do you see any outliers? Well, remember, outliers on box plots, they would be dots on the outside. And I don't see any dots on the outside. So I don't see any outliers. And then we're looking to see if our distribution is symmetric. Well, look right at the 50% mark, right at our median. The left side looks pretty close to the right side. And the left side looks fairly close to the right side there. So that means that both distributions are symmetric. So we would have to say, looking at our two distributions, there are no outliers and they are both symmetric. So we're going to continue on with our process. Other than that, that's all I wanted to say about this question. If you want to try this one out, be my guest. And if you want any help with it or have any questions over it, shoot me a question. But we're going to go ahead and start a test. So tomorrow, Wednesday and Thursday, y'all are going to do a test over confidence intervals for one mean and for two means. All right, y'all have a great day, and I will see you tomorrow.